let's start. So today is the 7th lecture, and things are going to start getting more interesting because we're going to talk a bit about sequence modeling and transformers, and also especially how they are related to robotics. So as a quick recap, we've been looking mostly so far at reactive policies, where we've taken like a single observation OT, feed it through our policy to get an action. And in principle, like this is like works in theory, but it breaks very easily in the real world because one snapshot usually doesn't kind of cover all the information about the state. There is kind of like two issues, right? So like one of them is like memory. With this kind of reactive policies, we might not know what we have done like, a few seconds ago, what decisions we have made or how the world was looking like, which might be relevant when we are like driving an icy road with an autonomous car, or from just like a single image observation, it might not be possible to understand how pedestrians are moving, in the scene, so that we don't run them over. If it's just like a static image, it's very difficult to estimate any velocities or motion. And there's also another issue of action smoothness, right? So our kind of one-step prediction models so far usually have been predicting just a single action for the next time step, right? And this can often, in the real world, lead to kind of like jerky trajectory that are like non-smooth, because like every decision is kind of like different, and so you can like get this kind of jerky oscillating behavior sometimes. And so today we're going to talk about some fixes we can do to address these issues, which involve sequence modeling and transformers. And that's what we're going to cover today. And so what it means is that, as I just said, right, like just having a single frame is usually like not sufficient, because in practice in robotics we are not operating in an MDP, but in like a partially observable MDP. And so to really understand the state, we kind of need to reason over the history or the trajectory. So like a sequence of observations and actions, and you can see also here, right? Like this is the kind of the trajectory probability formula we've been using through the lecture, and you see that how the policy we are modeling this is just this kind of like one-step policy model, like single step and reactive, and this is kind of like a fundamental mismatch between. Like the world is really like sequential, but like our policy like isn't. So the natural question then is like, what if we just model the whole trajectory directly instead of just like the next action? So how can we model these sequences, right? And the most general way to think about this is through the lens of autoregressive models. And the key insight here is that, and this is just kind of it comes from like the property of the probability, the chain rule, right? So it tells us that for any joint distribution, no matter how complex or high dimensional, we can decompose this into a product of conditional distributions. And so this means that we can get the probability of the entire sequence just as the probability of the first element times the probability of the second element, and so forth, autoregressively. Now, the key question we're going to like cover in this lecture is how do we actually model these conditional conditionals? Because if your sequence is like very high dimensional, it might be a high resolution video or like a complex robot trajectory, then this will become like very long, very, very like difficult, and we can't just use like a big lookup table. So the first logical tool that was kind of like invented to handle these conditionals are recurrent neural networks, or RNNs. The idea is very simple. You have like a hidden state that summarizes everything you've seen so far, and then you update it recurrently as new inputs arrive, which is great, as now you can handle variable length inputs. In practice, they have three kind of serious issues or failure modes. The first one is long-range dependencies. So to get information from step 1 to step 100, you have to propagate the gradients through all 99 intermediate steps, and then those gradients typically explode or vanish. And LSTMs kind of helped this, but didn't fully solve it. Then you have the parallelization issue. RNNs are very difficult to parallelize due to their autoregressive nature. And the third one is the bottleneck problem. So all your history gets compressed into a fixed size vector, no matter how long your sequence is, right? So there is kind of a fundamental information bottleneck that you can't hack your way out of. And so RNNs get you part of the way there, but the limitations are difficult in practice to scale. And by now, most of you are probably familiar with this, with the transformers paradigms, but I will give like a brief recap so everybody's on the same page. So instead of recurrence in transformers, we use attention. And the key property of attention is that it gets you O1 hop path length between any two positions in the sequence. Looking at the diagram, this means that the last word can attend to the first word directly in a single step, right, with a direct connection, without having to propagate through all the intermediate words. And so this simultaneously solves all three problems we just described for RNNs. Long-range dependencies are now trivial. Training can be fully parallelized because there is no recurrence, and there is no fixed size bottleneck because every token has direct access to every other token. Okay, so how does it actually work? So now you have a sequence of tokens, and for each token, you want to compute a new representation that incorporates information from the rest of the sequence. And so the question that the attention operation tries to solve is, which part of the sequence should you be looking at? And so essentially, this is what is being learned through attention, right? So you compute that relevance as the dot product between a query vector and a set of key vectors. Then you normalize with a softmax, so it sums up to 1. And then you just take a weighted average of the value vectors, and that's pretty much it. And now, what the nice thing about this is that you can think of this as kind of a soft differentiable dictionary lookup, where instead of committing to a single to one entry, as in a regular dictionary, you're simultaneously retrieving all values and blending them together, weighted by how much each key matched your query. And so because all of these operations are fully differentiable, now the model doesn't just learn like the representation, but also what is kind of the optimal search strategy. Now, there is one subtle important issue that in attention one needs to address, because the attention is computing this dot product between the tokens. It's fundamentally a set operation, and it treats all the inputs without any notion of order. So this means that the robot picked up the spoon, and the spoon picked up the robot would produce identical attention patterns if you don't do something about this. And the fix is to add positional encodings. So you inject order information directly into the token representations. And there are two main ways how you can do this. The original approach from the attention is all you need paper is to just add a fixed vector to each token embedding before it enters the transformer. And it's pretty simple. It works well. There's absolute positional encodings. But there is kind of one limitation, that if at test time now you have longer sequences than the ones you trained with, this will fail, right? Because it's now out of distribution. The second one is relative positional encodings, which solve this issue a bit more elegantly. So instead of encoding the absolute position in the sequence, you encode the distance between the tokens. For example, it could be a bias that you add directly to the attention score. So this means that in our example, the word spoon attending to robot will know that it's just like 4 steps away, regardless of where in the sequence they are. And crucially, like this generalizes then to kind of unseen lengths. And many of the modern foundation models build upon kind of similar extensions based on relative distances. All right. Now let's look at how the original transformer put all this together. So this model was designed for machine language translation. So you have a source sentence, and then you want to produce a target sentence in a different language. And then this kind of breaks down into first understanding the source sentence and then generating the target. And hence they have this encoder-decoder split. The encoder uses bidirectional self-attention. So every token can see every other token, past and future. And this kind of makes sense because you have the full input available and you want to get your richest possible representation of each token. And now for the decoder, this is very important. It uses causal self-attention, where each token can only attend to itself and the tokens that came before it. And then we have this kind of like triangular mask there on the right that is just setting future attention scores to negative infinity before softmax so that they zero out. And this is what makes autoregressive generation possible. At each step, you only can condition on what you have already generated. And then in the middle, you can see the cross-attention, where in the middle of the decoder, where kind of the encoder and decoder talk to each other. So the decoder kind of asks, given what I've generated so far, what from the source is relevant for me right now? And so this means that the queries come from the decoder and the keys and values will come from the encoder. Cool. How do we train this? Very simple. We use something called teacher forcing. The idea is that during training, we don't care if the model makes a mistake at a certain time step. So instead of feeding the model its own potentially wrong prediction, we always feed it the ground truth of the preceding tokens and ask it to maximize the likelihood of the next correct token via cross-entropy loss. And kind of the nice thing about this whole operation is that we just need one forward pass to compute all sequence losses with transformer, whereas with the RNNs we would need to do one forward pass for every token. All right, so before we can apply any of this to robotics, we need to ask a more basic question: what is even a token? How do you discretize your input into units that this transformer can operate on, right? And so starting with language, because that's where transformer originated, we have two kind of like obvious extremes, right? So the first one is characters, to use characters, right? This would be a tiny vocabulary, and with sequences would be very large, and the model would need to learn like very hard to model all of them, right? And then you have words on the other extreme, where sequences would be like short, and each token would be meaningful, but then you would have the issue of like, what do you do if you get an unseen word, right? Like you might not be able to represent it with your pre-trained vocabulary. And so neither extreme like works well, and ideally you want something in the middle, so units that are larger than characters but smaller than words. and that can handle unseen vocabulary kind of gracefully and keep sequence lengths manageable. Because the attention operation is quadratic, right? And so that's what subword tokenization gives you. So if you want this something in between, typically we use this algorithm called byte pair encoding, or BPE, which is essentially a bottoms-up clustering approach for text. So the logic is very simple. As you see in the pseudocode here, you start with the most basic building blocks, all unique characters in your data set, and then you iteratively look for the most frequent pairs of adjacent tokens and merge them into a single new token. And you repeat this k times until you've built a vocabulary of the size you want. And what happens in practice is that common subwords then get merged early because they appear everywhere, and then this keeps our sequence length short, which is, again, critical because the transformer's memory usage is quadratic. And the advantage of this is also generalization, because now if you see a completely new word at test time, you can probably break it down until like until one common subword unit into a sequence of kind of like known subword unit. Here is a concrete example for one sentence. The robots melted the robot's unbearably cheesy fondue. And here in this animation, you can see how BPE works in this single sentence and how the subword tokens get merged. And then the result is that we go from 54 characters compressed down to 34 tokens. So like a 37% reduction, so that's great. One key detail that you should know about BPE is that the compression factor scales with your corpus size. So the more data you train your BPE tokenizer on, the more common patterns will get merged, and the shorter your sequences will become, and therefore more efficient your transformer. And so modern LLMs trains on kind of internet scale data, maybe with a vocabulary of like 100K tokens, you'll get like 3 or 4 times kind of like compression rates compared to this thing. All right. So how did we get from the original transformer to scaling these 2 large language models? I want to briefly touch upon a few engineering decisions that made them work at scale. The first is architectural simplification. So modern LLMs like GPT drop the encoder entirely and use decoder-only models. It turns out that if you train a decoder on next token prediction, it's simpler to scale, and with enough data, a causal decoder can just learn to represent the context just as well as the bidirectional encoder. Then the second one is extending BPE to the byte level. So instead of operating on characters, you operate on raw bytes, which means your base vocabulary covers literally every possible input. And I know I just told you in the previous slide that BPE generalizes to unseen words, and that's true. But with byte level BPE, you can also generalize to, let's say, emojis that we couldn't cover with the pseudo algorithm I just showed you before. And then there are 2 kind of engineering tricks or innovations that made training on longer sequences more practical. One of them is ROPE, rotary positional encodings, which is kind of an elegant solution to the positional encoding problem, where instead of adding the position vectors to the embeddings, it rotates the query and key vectors by an angle proportional to their positions, so that the dot product depends only on the relative distance between the tokens and not their absolute positions. And then flash attention solves the memory bottleneck. So The standard attention requires materializing the full n times n attention matrix, which is n squared in memory consumption. And then for very long sequences, this becomes like a limiting factor. And then with flash attention, this tiles the computation into fast SRAM so that you never actually store that matrix, getting your memory consumption down to O of n with the same result. So let's take a step back and see how people scaled up transformers and what scale bought us. Back in 2018, with GPT-1, we were kind of still very much in the pre-training plus fine-tuning regime. So you train on 1 billion tokens, but the model wasn't actually useful for any specific task until you did like supervised fine-tuning on some narrow task data set. Then you move to GPT-2 in 2019, so a year later. And then we scaled the model with 10 times the parameters and 10 times the tokens. And then we started to see zero-shot generalization, where the model starts being able to perform tasks that it was not explicitly told to do, because it has learned enough kind of structure of the world through text, right? And then in GPT-3 in 2020, with 175 billion parameters and 300 billion tokens, you have like this phenomenon where in-context learning emerged, right? So you give the model a few examples in the prompt, and then it figures out like the pattern of your context pairs and is able to apply this to new inputs without any gradient updates. And the surprising thing is that this kind of emerged as it just appeared as a consequence of scale. And this connects directly to what Rich Seton called the bitter lesson in 2019, where the argument is quite simple that he made. So it basically states that if you look at the history of AI over the past 70 years, then the methods that ultimately win are not the ones with the most clever domain knowledge or the most carefully hand-engineered features, but these are the ones that actually scale with compute. So like no matter if in chess or in speech recognition or Go, in every single case, usually like handcrafted approaches were competitive for a while, but then ultimately like more general methods with more compute eventually overtook them. And then this plot from the GPT-3 paper is kind of like a perfect illustration for this, where you can see that for this model with like just 1.3 billion parameters is like essentially flatlining, no matter how many examples you put in the prompt. But then once you scale it to 175 billion parameters, the model becomes a few-shot learner. And again, like this is, not because somebody engineered it to do it so, but it just emerged through scale. And if this is true in language, the question, that the field is trying to answer today is also what emerges when you scale up robot data, right? So if scale is what matters, the next question is how do you scale optimally? Right? And so for a few years, especially after, with GPT, the first GPT models, the community seemed to think that just making the models bigger was the primary approach. And this is what the Chinchilla paper from Hoffman et al. Worked out very precisely, that this is not the case. And the key finding here is that given a fixed compute budget, you should scale your model size and your data in equal proportion. So now if you look at the left plot over here, you can see the envelope for various model sizes across different compute budgets. And at low compute budgets, the optimal choice is actually a smaller model. Right? So a 75 million parameter model trained to its optimal point sits on the envelope at low flops, while a 10B model trained with the same compute budget would still be under-trained and sitting above the envelope. And now in the center and right plots, where we plot the scaling model size and training against compute, we can see, for example, that GPT-3 was actually under-trained, meaning that it was too big for the amount of tokens it was trained on, compared to the optimal scaling frontier, which is this dashed green line that was derived in the Hoffman chinchilla paper. The paper also found out that you need roughly around 20 tokens per parameter for compute optimality. All right. So this slide shows you something useful in practice that falls out of this scaling laws. And this is that you can actually predict how a larger model will perform before you train it. So the idea is simple, right? So before you commit your entire compute budget to one big expensive run to train your next GPT-6 model, you first do a bunch of cheap small runs at different model sizes and compute budgets, and then you can kind of like extrapolate what the performance of your bigger model will be. And you can see that by kind of like following the line of this isoflop plot. And then the right plot here, we plot the training tokens against the model size for some different models. And you can see how, well, the first GPT models were all undertrained, right, according to the optimal frontier. And then kind of Llama 1, 2, and Chinchilla kind of like were more on the more optimal compute frontier. And then you see the Llama 3 is like way above the frontier, right? So it's trained on more tokens than the compute optimal like formula would suggest. And the question is like, why did they do this, right? Because the motivation behind this is that the compute optimal, to be compute optimal is the right strategy if you only care about the training costs. But if you're going to serve a model to millions of users, then you actually want a smaller model that's cheaper to run at inference, even if that means overtraining it slightly. And so that's why they made this kind of deliberate choice. All right, so we've established that transformers are incredible general-purpose sequence models. We have LLMs, they scale predictively, they have emerging capabilities at scale. But for a robot, language is only half the story, because for a robot, it has to perceive the world to do decision-making, right? So the next natural question is, how can we extend our transformers and LLMs to handle visual observations? So maybe you already remember this from one homework assignment, but very like kind of recap about image tokenization. The key insight from the vision transformer paper, from Alexei, who I overlapped with in Freiburg when he was a postdoc there, by the way. And Lucas Bayer, who will come later in the course to give an in-person guest lecture, is quite simple. So the idea is that you treat image patches as tokens. And so you take your image, like 224 by 224, split it into your grid of 16 by 16 patches. That gives you 196 patches. And then you flatten each of these into a vector, project this linearly, and then you add a positional encoding to tell the transformer where in the image each patch came from. And you're done. So now you have 196 tokens that all look exactly like text tokens to the transformer. And so essentially, this is kind of similar to the philosophy of the BPE we saw for language, right? We kind of try to find the right unit, turn it into a vector, and then we let the transformer figure out the rest. And so for language, kind of subwords was this unit, and for images, it's patches. And because now the interface is identical, you can start mixing and matching these text and visual tokens in the same sequence. So So now we are at this kind of elegant situation where everything is a token. But this kind of raises the question, if we just concatenate this kind of image and text tokens in the sequence together, then the transformer has no idea which one came from an image and which one came from a text and how they relate, right? And so, for example, ideally, we would want our model to be able to relate text tokens to, let's say, the word apple with the visual tokens corresponding to, let's say, the bounding box of an apple in the image, so that we can later ask our robot to pick up an apple and with a language instruction that it kind of understand what we are telling it to do, right? So, so how can we teach the model to align these two modalities? One of the first answers to this question came from OpenAI's CLIP model. CLIP trains two separate encoders, hence the two towers, a VIT for images and a transformer for text, and then learns to align them in a shared embedding space using contrastive learning. And so it's very simple. You have a batch of n image text pairs scraped from the internet, and then you encode all of them into a n by n matrix where you compute the cosine similarities. And then you have a kind of like a temperature parameter to control the entropy or the sharpness of your distribution. Yeah, and this way, with this contrastive alignment, you get now visual representations that semantically are aligned with language. So now the image of apple and the word apple will end up nearby in the embedding space of this model, which is exactly what we wanted. All right, sorry. So now this is another approach to aligning vision and language, but with a different goal. So CLIP was about learning a shared embedding space between the two modalities. And now Lava asks a different question. It asks, how do we inject visual information directly into a pre-trained LLM so that it can now reason over images in the same way it reasons over text? Because with CLIP, we didn't have like an LLM, right? And so the answer here is to do early fusion. So you take your image, you run it through a frozen CLIP vision encoder. So you get your patch embeddings. You pass those now through a small trainable MLP connection layer to fit them into the right dimensionality. And then you just prepend them to your text token sequence. And now the LLM runs the standard self-attention over the entire unified sequence with no architectural changes whatsoever. And so here, the key design choice is what is frozen and what is trained. So the CLIP encoder stays frozen all the time. So you leverage all the pre-training and you're not touching this. And then the MLP connector learns how to project the visual embeddings into the LLM's token space. And then the LLM gets fine-tuned on visual instruction data, teaching the model how to follow instructions that are grounded in images. Then there is a third way that comes from the Flamingo paper called late fusion via gated cross-attention. And this is kind of contrasting to the Lava's early fusion approach. The key distinction is how and where vision gets injected into the language model. So in Lava, the image tokens are prepended to the text sequence, and then everything goes through the same self-attention. Flamingo says, what if instead of keeping the LLM's self-attention operating purely on text, can we inject visual information at every layer via gated cross-attention? And so concretely, what they proposed here is they keep the vision encoder frozen, and then they kind of compress its output with a perceiver resampler into a fixed size set of keys and values. And then at each layer of the LLM, there is a new cross-attention block inserted where the text tokens act as queries and attend to those visual keys and values. And the elegant part of the whole approach is the 10H gate, because it's initialized to 0. So that means that at the start of the training, the cross-attention contributes exactly nothing. So the model behaves identically to the original LLM. And then as the training proceeds, this gate starts to gradually open up and the visual information flows in. And so this is a very principled way to preserve the pre-trained language's abilities while slowly learning to incorporate vision. Okay, so Lava and Flamingo both share the same fundamental assumption. You start with a pre-trained language model, and then you somehow add vision to it, right? But there is a third approach that asks, what if we just throw away all of that and train everything jointly from scratch? And that's the idea behind native multimodal models. So instead of adapting a language model to handle images, you train a single unified transformer on all modalities simultaneously. So images, audio, video, text, it doesn't matter. You interleave them in any order, in any combination. And so the input now is completely flexible. You can have image tokens followed by text, audio followed by video, or any arbitrary mix and combination. And so the model doesn't have, let's say, primary modality with others bolted on. It just sees a sequence of tokens and learns to reason over all of them jointly. The appeal is obvious because in principle, this is the bitter lesson kind of like scaled to the extreme because there is no architectural bias toward any one modality. But obviously is the most expensive one to train. So most of the current VLMs that you know are related to one of these three paradigms we just covered. So early fusion on the left, which is basically a pre-trained LLM plus a vision adapter, is also the most popular one in open source community with Lava, PalyGemma, Gemma 3, and so forth. The recipe is the same. You just swap in a better vision encoder, better base LLM, and iterate. Then late fusion in the middle is a bit of a smaller family. And then natively multimodal on the right is where big proprietary models are converging, like Gemini, GPT-4o, GPT-5, and also increasingly some of the bigger open source frontiers like Llama 4 or Qwen 3.5. The trade-off here is essentially flexibility versus versus scalability. So early fusion allows the richest cross-model interaction because the images and text mix freely through self-attention, but then you have to like fine-tune the LLM and risk degrading its capabilities. Late fusion preserves the pre-trained LLM perfectly, but constrains how vision and language can interact, since they only communicate through this cross-attention pathways. And then native multimodal removes all of the constraints, but you pay the cost of training everything from scratch. All right, so we went from transformers for better language translation to LLMs as general reasoners to VLMs and native multimodal models that can perceive and reason about the world. And every step in this progression was kind of the same play. We find the right way to tokenize a new modality, feed it into the same architecture, and scale it. Text and images, then audio and video, right? So now the question is obvious. Can we do the same thing for robot actions? Can we tokenize actions, throw them into the same sequence as observations and language, and train a model that can reason over all of them jointly? And this means that we can view robotics as a multimodal sequence prediction problem where we have language tokens, image tokens, and instead of kind of answer text tokens, action tokens now that can command the robot's motors. And so basically, we can now run the same next word kind of prediction architecture, and we can, without changing anything fundamental, but just adding like new robot action tokens. And by using now the attention mechanism, right, we can now, we are asking what from my entire history is relevant to what I should be doing right now, right? So with the attention, we are kind of like also looking to solve one of these like memory issues that we were mentioning in the beginning. So how can we tokenize robot actions? Because actions are continuous and they're not discrete, right? So the first way how we can go around this is to discretize them. The first approach used by models like RT2 and OpenVLA used a simple per dimension, per time step binning scheme. So the first, it's pretty simple. First, you do quantile normalization. So for each action dimension, you compute the first and 99th percentile of the action distribution across your training data, and then you clip to those bounds. And then by normalizing into the range -1 to 1 using the quantile bounds, the discretization is identical and comparable across every robot and every dimension. RT2 originally used min-max normalization, but that doesn't work really well with outliers, as this can result in having to fit the majority of your distribution into, let's say, the first 3 bins, and then waste the remaining 253 bins to represent this one outlier. So we discretize then each action dimension, and we have with the quantiles, and we have normalized this into -1 and 1, and then into we discretize them into 256 bins. And then we finally inject this into our LLM vocabulary, right? So now for each action dimension, we have like this 256 bins. And how do we connect this with our LLM? One common approach is what you can do is you can override the least frequent tokens in the vocabulary. So let's say if we have 256 action tokens, the least 256 frequent tokens in your vocabulary. These are often some, I don't know, weird Chinese symbols or characters. And you can override those now with your new action tokens to connect your LLM with your action tokens. And at this point now, the model is just can do next token prediction with the same cross entropy laws and the same architecture as the LLM. So remember, right at the start of the lecture, we identified these 2 problems with the reactive policies, right? So the first one was like memory, where like a single observation can capture the full state of the world. And then the second was action smoothness, making independent decisions at every time step produces this kind of jittery movements, right? Or incoherent behavior. And so we kind of address memory through the sequence modeling problem and the transformers. And action chunking is the direct answer to the smoothness problem. So the key idea here is that instead of predicting just the next step, we ask the model to predict a trajectory of future actions, so the next K actions. So the most basic version you can see at the top of the diagram, where we query the model once. It gives us a chunk, let's say the next 4 time steps of the trajectory. We execute those, which gives us a more fluid motion since all 4 actions were planned at the same time or at once instead of sequentially with a one-step model. And after that, we requery the model to give us the prediction of the next 4 actions, right? And so forth. Now, if we extend this to longer horizon chunks, let's say to accommodate higher frequency control, because you have a humanoid or something, let's say we have now 100, like an action chunk of 100 that we are predicting. There is one failure mode where if we like execute all 100 actions before we requery the model, like in the meantime, like in this 2 seconds, the robot is blind, right? It's not updating anything, and bad things could happen in between, right, that we didn't account for. And so one solution for this is to do temporal ensembling, which you can see at the bottom, where you requery your model at every time step and maintain multiple overlapping predictions for every time step. So for any given time step, now you can combine predictions for multiple queries with exponentially decaying weights. And now this gives you the smoothness benefits of chunking while staying reactive to new observations at every step. And ACT is the paper from Tony Zhao, Cheng's co-founder at Sunday Robotics, if you remember the guest lecture from last week. And in this paper, they introduced action chunking for dexterous bimanual control. The setup is a bimanual Aloha robot doing 50 hertz control. And the model predicts chunks of 100 actions at a time. So as the robot is doing joint control with 14 degrees of freedom, the model is predicting 1,400 values at every forward pass. And this work showed that this action chunking works really well when you're doing really dexterous tasks like this battery insertion, which requires very precise, coordinated two-arm motions with very little tolerance for any jitter or unsmooth behaviors, where like a reactive policy making independent one-step decisions at 50 hertz would struggle quite a bit with doing these tasks. But by having this policy that is planning like kind of smooth, like 2-second chunks of trajectories, you can see that it can execute it much more fluidly. All right, so we have established that larger action chunks are helpful to do smoother, high-frequency dexterous control. But ACT was not using any LLM, and it was not predicting 1,400 values or tokens autoregressively. Because like once you want to do this with a VLA, this starts to break down very quickly, especially the higher frequency you go. Because the tokens start to look very similar to each other. So basically, the higher the frequency you go, the less difference is there between one step to the next, right? Like it's such high frequency that you look at one frame and the next one, and there's like almost no movement happening in between, right? And the learning signal for an autoregressive model comes from the new information each token provides. And so when the tokens are highly correlated, the marginal information content of the next token approaches basically zero. And now this means that the model, and this is very important, can achieve a low prediction error by simply learning to copy the previous action token, which prevents it from learning the actual dexterous skill. And so here on the far, you can see how performance starts to degrade once we train VLAs autoregressively at higher control frequencies like 10 hertz or 20 hertz with this naive binning tokenization scheme that we just explained. So the obvious solution is to do some sort of compression. Right? So instead of tokenizing every individual action, you want to find a more compact representation, like the subwords in the original BPE tokenization, that captures the meaningfully structure of the motion. Right? So we want to find this equivalent kind of representation of the subwords for BPE or the patches for images for our robot trajectories. Right, so units that are larger than a single time step, but like smaller than an entire trajectory. And so how can we best compress data, right? We just covered in LLMs, we can use BPE, which works well for discrete domains, but as we just said, like we have continuous data streams for robotics. We could use like maybe like VQ VAEs, but then this is one more model and more complexity to train. And the key idea here, what you can do to get more efficient compression, is actually borrowed from signal processing, which is to use the discrete cosine transform. So if you ever wondered how, for example, JPEG compression works, this is essentially it. Robot action chunks are smooth trajectories, and smooth signals have most of their energy in the low frequency domains. So when you apply DCT to each action dimension, you're moving from the time domain to the frequency domain. This gives you a sparse frequency matrix where most high frequencies are near zero. You can then scale and round these coefficients, flatten the matrix with the low frequency components first, and then you can run BPE on the actual resulting integer sequence. And so what BPE will do is it will squash the zeros and merge the frequent coefficients combinations, giving you now a compact sequence of dense tokens that you can plug directly into your existing vocabulary. So what are the results when we train a VLA with this approach? Looking at the left plot, we can see that our performance now doesn't break after 5 Hertz for an autoregressive VLA. We can actually keep improving performance. And the compression is doing exactly what it should, right? It's preserving the information that matters and disregarding redundant high-frequency correlations. And on the right side, you can see what this compression is buying us at test time here. We adapted pi0 to do pi0 to do autoregression using this fast tokenization scheme we just introduced on top of the polygemma backbone, and compared it against the pi0 from physical intelligence that is using flow matching instead of autoregression for action generation. And you can see that our model converges 5 times faster to the same performance. This was a collaboration I did with physical intelligence during my time at Berkeley. And one of the coolest results here is that we trained a VLA on the Droid dataset that could do zero-shot language tasks in the wild. So we tested it in unseen kitchens across Berkeley, Stanford, and University of Washington, and it worked really well. And also we were able to do now complex long-horizon bimanual manipulation tasks like laundry folding at 50 Hertz, essentially now pushing along both axes of generality and dexterity, which typically are in tension, right? Because either you build like kind of specialist policies like ACT that are very precise but narrow, or generalist policies like OpenVLA that are broad but usually not dexterous enough for fine manipulation. And this kind of work kind of make advances across both. And also an output of this work is a good off-the-shelf tokenizer that's available on Hugging Face that is useful for like training VLAs, if you want to check it out. All right, so to conclude today, we started with a simple observation. Reactive policies are fundamentally limited because one snapshot of the world can capture the full state, right? And independent per step decisions produce jittery behavior. And the fix we addressed in this lecture is to reformulate robotics as a sequence modeling problem. And then we went around building this toolkit, right? Transformers gives us a scalable architecture for sequence modeling with O1 access to any parts of our history. Scaling those transformers gives us LLMs with emergent capabilities. We have seen how to extend them to vision through early fusion, late fusion, or native multimodal training. This gives us VLMs that can jointly reason over images and language. And then the final step, extending all of that to robot actions, which turns out to be non-trivial because naive tokenization breaks at high control frequency. and you need compression-based approaches like FAST to make autoregressive action generation actually work at the frequencies the robots require. The central insight running through all the lecture is really the bidder lesson applied to robotics. Find the right representation, use a general scalable architecture, and then let the data and compute do the work. And with this, thank you for your attention.